All right, so good morning, everyone. I guess it's afternoon now, but I hope everyone's having an amazing day. And my name is William Thang, so I'm the co-president at Project Tech Conference's Seattle branch. So unfortunately today I'm not joined by another executive member, but usually you'll see like in our other events, we'll have like at least 2 or maybe like 3 other exec members. So on behalf of the executive team, we appreciate each and every one of your attendance at PTC Seattle's track of artificial intelligence. So we organize a bunch of keynote talks and workshops, and today's workshop will be led by the Interactive Intelligence team from the University of Washington. So the Interactive Intelligence team works to explore the connection between reinforced learning, embodied artificial intelligence, and neuroscience. So to learn more about the Interactive Intelligence team, make sure to check out their website and Instagram account. I'll post that in chat right now. See. So here is their website, and then their Instagram is. Also, just a quick note, if you guys have any questions, put it in the Q&A box instead of the chat. But if that's not popping up for you guys, you can just put it in the chat instead. Yeah, okay. So today's workshop will cover the topic of neuroscience and AI for the development of human-like intelligence. So this will be exploring the various implementations of memory in modern machine learning, and then we will relate those techniques to neuroscience's current understanding of how memory works in our own brains. So our 2 workshop leads for today will be the president of the Interactive Intelligence team, Chetan Imran, as well as the neuroscience lead, Jana Hong. So after the main session, we'll have a quick Q&A period where you can ask any questions to be answered live. And if you have any questions during the main session, feel free to send your questions, as I said, in the Q&A box. But if that's not there for you, then you can put it in the chat as well. So yeah, now I'll pass it over to the Interactive Intelligence team to introduce themselves and to get started on today's workshop.
Hello, I'm Chetan, and yeah, I'm the captain of the Interactive Intelligence team, and Jenna.
Hello, my name is Jana, and I'm the neuroscience major in the Interactive Intelligence team.
And yeah, so we are studying how artificial intelligence and machine learning can learn from and work with neuroscience to make artificial intelligence more like how humans learn. So today we're going to be presenting about memory and attention specifically. So we're super excited. So to start off, well, in general, the first things we're going to talk about are memory-like structures in deep learning, just some basic neural networks that recapitulate different aspects that we might call memory in the brain. Then Jana will talk about the neuroscience of memory, and then we'll go back to revisiting memory in artificial intelligence, but this time looking at attention, which is definitely strongly related to memory as well. So first, memory in deep learning. So yeah, and if anybody has any questions along the way, this does assume that you know a little bit about neural networks. But if there are any questions about that, then please let us know. So the first thing we're going to introduce is called a recurrent neural network. So the base of a neural network is that you have some input data, some numbers that represent something about the world, and then you have, and if it's not naturally a number, like maybe it's a picture, you would have to turn it into some numbers, like values for the colors, and then you have some math in the middle, and then you have some output at the end, and that output should describe some prediction about the world. So a recurrent neural network is a particular kind of neural network that this X is going to be our input, and then this A is going to be all that math in the middle, and then H of T is going to be not the output. The output is actually this horizontal arrow, but the H of T is going to be a hidden state. So it's, in the middle of doing all that math, we're going to take the output there and then send it back into the network as an input. So what happens with a recurrent neural network is that in a normal neural network, everything goes in and then out, and then you get an output. In a recurrent neural network, we're continuously feeding back the input from the prior input. So it's really good at processing sequences. So if you have a string of words and you want to continually evaluate what the next word is going to be, but that depends on what all the previous words have been, then this is a good choice for that, because you don't want to forget what all those previous words were, because otherwise you don't know what the next word's going to be very well. So, and if you just predict what the next word is going to be based on the last word, you're going to be missing like the whole story, right? So you won't have a good prediction. So a recurrent layer is meant to do that. Here's some problems though. So the problem is that this hidden layer that we keep passing into the next layer gets overwritten over time. So the further along in our story that we get, trying to predict the next word, the more we forget the beginning of the story. So if you have a really long sentence and you introduced the subject of the sentence, like the first word, by the end of that really long sentence, your neural network's going to forget all about your subject of your sentence. So it's not really doing anything like what your brain might do, at least because we don't forget things like that. Like when we're talking, if we have a really long sentence, we don't forget that we're talking, we don't forget what we're talking about by the end of it. So this might be a good example of a short-term memory captured by this hidden layer that we keep passing through, but it does not work very long. So then people came along in deep learning and they said, okay, well, let's make it harder to forget. And they did that by introducing this concept of a cell state. And these are called long short-term memory networks, LSTMs. And this cell state is basically difficult to write to, but easy to read from. So we're going to keep doing what we did where we pass that through. And it's just, so that's this like top horizontal bar here. We're going to keep passing that through. It's just harder to write to, so that it's harder to forget what you were talking about in the beginning. But nevertheless, it doesn't solve the fundamental issue of your hidden state will get overwritten the further you go. So if you're reading a book and maybe you just need some context from paragraphs before to understand what is currently being said, it probably will not be able to handle that. So then some other smart people came along and they said, okay, forget this passing through the hidden layer that's going to get overwritten every time. Instead, let's just make a mapping of every single word in our sequence to every single other word. And then let's pay attention to specific words in all of that prior context that we need to. So that's called the transformer model. And in general, these large language models are really popular right now. So for example, LSTMs used to be used for Google Translate up until about 2016. But then transformers came along and they replaced it with a transformer because it does better with these problems that we're talking about. However, the question is like, okay, now we have something that can pretty well generate words and sequences that make sense given all this prior context, and they don't have this problem of forgetting. But how well are these actually knowledge bases? How well do they know what they're talking about? So, for example, like this sentence, President Abraham Lincoln died in the year 1865, a year that is still a matter of debate. I don't know if that's really a matter of debate, but the neural network doesn't know that. So in general, being able to represent knowledge very fluidly, like with these large language models, instead of say using like mathematics to try to describe something, it gives you a lot of flexibility, because math can answer like this ambiguous question, like the tallest man in the world is, like there's many possible things you could say after that statement that would make sense. So there's so many possible answers that you can't use like math to answer, to solve language, right? But at the same time, you can't use language to solve math very well. So the fluidity of the queries is a double-edged sword. Okay, so that's it for deep learning survey.
Okay, so you can go talk more about memory and neuroscience. Next page. Oh, we can go, yeah, thank you. So memory, basically, it feels to us like a single function, but it's actually not. And memory has several distinguishable components that work together, as in the figure. And distinguishing the different types of memory is useful for studying the anatomy of memory. And different parts of the brain support different types of memory. And this chart is a brief summary of memory, beginning with the type that holds information for the shortest duration to the one that holds it for the longest. And we will kind of go over each one of these in the next slides. And next slide, okay, thank you. Sensory systems receive and briefly hold for about 0.2 to 2 seconds about many details of sensory information represented as transient changes in the sensory cortex. So attention, which is a mechanism that selects which of the information available to us we examine in more detail, selects the features of sensory experience to transfer to short-term memory. And sensory memory exists in sensory regions of the cerebral cortex, and the bold labels, the somatosensory cortex and visual cortex, indicate examples of sensory cortex where that memory resides. And then the next slide, we're going to go into short-term memory. And short-term memory makes information immediately accessible without manipulation or retrieval from long-term memory. And it can typically store about 7 simple memories. For example, the number series like 2387530, those are 7 digits, and that would fully occupy the average short-term memory. And so would the years like 1882, 1875, 1918, and so on. But you can the average human being can memorize up to 7 years. And this was created by a guy named George Miller, and some people call it the magical number of 7. But anything above 7, it's going to become like a random guess, because that's how our short-term memory works. And so the brain transfers some information from short-term memory to long-term memory through a process called consolidation. Short-term memory relies on temporary changes in the prefrontal and parietal cortex. So the pink areas in this figure shows the parts of the cerebral cortex implicated in short-term memory by functional MRI evidence. And according to this evidence, approximately the same areas on both sides of the brain support short-term memory. And then the next slide, we're going to go into long-term memory. So very briefly, long-term memory stores an enormous amount of information and can hold much of it for a very, very long time. For example, an entire lifetime. And long-term memory starts with information transferred from short-term memory via something called consolidation. And consolidation requires the hippocampus and probably nearby areas of the temporal cortex. So on the next page, I'm going to dive in a bit deeper about long-term memory. And as this chart shows, we can divide long-term memory into declarative, also known as explicit memory, and procedural memory, which is also called implicit memory. So declarative memory consists of 2 types of memory, both episodic and semantic. Episodic memory is called an autobiographical memory, and it holds information about events and details of your own life. And semantic memory, on the other hand, holds objective facts. For example, George Washington was the first president of the United States. And semantic memory also holds meanings of words and vocabulary. And on the right, you see procedural memory, which holds information about motor skills, for example, riding a bike, and also conditioned responses. I don't know if you guys have heard of Pavlov's dog, but it's like a dog salivating when they hear a bell that had sounded repeatedly in the past before they got food. And this type of memory is also called priming. And to move on to the next slide, we're going to observe the different types of long-term memory furthermore. So once information enters long-term memory, there are permanent changes in a distributed network of several brain areas holding that memory. And this panel summarizes the regions of the cortex implicated by fMRI data in storing long-term declarative memory, both episodic and semantic, which is shown in the green. And in the pink, you see long-term memory of vocabulary words, which is, as I mentioned earlier, it's a type of semantic memory. And this relies on changes in the cortex in the anterior temporal lobe. And then in the purple region, which is the frontal premotor cortex, long-term procedural memory consists of changes in an area of cortex in that area. So it's not shown in this figure yet, but there's also regions like the basal ganglia and the cerebellum, which also play a role in procedural memory. It's not here because the exact nature of that role is not clear. Okay, on the next page. So current theories of the hippocampal function goes as follows. So as I mentioned earlier, hippocampus is required for the long-term memory. So information about the world first reaches the hippocampus at the dentate gyrus, a region that runs along the bottom edge of the hippocampus. And here the representation is prepped to be in a form that is more flexible to memory storage. And the dentate gyrus then sends connections to an area called the CA3, which is in the middle. And CA3 has extensive recurrent connections that give it like a hot field network-like effect. And hot field network is basically saying that one set of neurons triggers the activation for the rest of the firing patterns, like an attractor, if you've been in physics before. And this area then sends output to another region called the CA1, which acts as a relay station. It sends the remembered information back to the rest of the brain. So what's interesting about the final step is that the projections out to the different areas of the brain are believed to facilitate the copying of memories. So in this way, the CA3 acts as a warehouse holding onto memories until they can be transferred to other brain areas. And it also does this by reactivating the memory in those areas. So for example, how do you study for an exam? You might use repetition, right? So likewise, the hippocampus helps the rest of the brain memorize things using the same strategy used to study for a test, repetition. And by repeatedly activating the same group of neurons elsewhere in the brain, the hippocampus gives those neurons the chance to undergo something called Hebbian learning, which is a fancy term for neurons that fire together, wire together. And also there's a theory that over time, information from certain memories that are temporally stored in the hippocampus can be transferred to the neocortex during sleep. So that's another reason why sleep might be very important for your memory. And this process is referred to as cortical integration, and it helps protect the information stored in the brain. So we're gonna dive into some fun case studies in neuroscience. So if you've ever studied neuroscience, you'll most likely hear about the case studies of Henry Molaison, or famously known as HM, and people like Phineas Gage. So Henry Molaison, he's a guy that was famously known as HM when he was alive to hide his identity, and he was a patient with epilepsy. So when he turned 27 around the 1950s, surgeons removed the anterior 2/3 of his hippocampus and the mediotemporal cortex near his hippocampus on both sides. And the damage to Molaison's hippocampi and temporal lobes left him unable to form new declarative memories. His old declarative memories were intact. For example, he remembered his wife and was always happy to see her, but he forgot what was happening very quickly, even though he could still hold brief conversations. He could learn to do new physical tasks like jigsaw puzzles and finger mazes. And as he practiced these tasks, his performance improved at a normal rate. So even without the hippocampus, it seemed like his procedural memory functioned apparently normally. And even after much practice, however, he did not remember ever having done these tasks previously. So this HM case illustrates that the hippocampus and the mediotemporal lobes are necessary for forming new long-term memories, but not for holding new short-term memories or long-term procedural memories. And through HM, we first discovered that the hippocampus is a declarative memory formation hub. And next slide, we're gonna learn more about Clive Waring, and there should be a picture here, but oh, there it is. Thank you. Clive Waring was a skilled and accomplished professional musician, and around the 1980s, when he was around 40, 45 or 46, he was at the peak of his career, but unfortunately, he contracted herpes, and the infection destroyed his hippocampus bilaterally and caused a great deal of damage to his frontal lobes. And as a consequence of this damage, he was unable to form new long-term memories. And he also lost much of his episodic memory after he was in his 20s. So despite the profound memory deficits, he maintained much of his procedural memory. For example, when he was still like front of a choir and he could conduct them at a professional level, and he could also play music expertly. So this case illustrates again that the hippocampus is critical for changing short-term memories into long-term memories via consolidation. And it also shows that the frontal cortex is important for storing episodic memories. And a little bit more about Clive Waring. One consequence of this brain damage that Waring suffered is that he repeatedly felt like he has just awakened and was recently conscious of his surroundings and situations. He forgot that he has had this insight very quickly, but then he has it again and again and again. For example, he will write repeatedly in his journal something to the effect that, now I'm alive, I do live every couple of minutes. And he can repeat this observation seemingly endlessly. So it's very an unfortunate situation. And next slide. Yeah, so memory can definitely be compared to a computer in which information is stored as an input and then stored, as I said earlier, in the hippocampus as a throughput and retrieved as an output.
Okay, so that was super cool. So now we've learned a little bit about memory in deep learning and memory in the neuroscience world, or like, real memory. But they seem pretty different. They don't seem like they're that similar. So one more thing that we're going to look at is attention in deep learning. And one researcher at DeepMind, which does a lot of reinforcement learning work and research. His name is Alex Graves, and he says memory is something like attention over time. That claim is not founded on neuroscience. It's just sort of an observation, and whether or not it's true is an interesting question. So one of the things Alex Graves has contributed to is something called neural Turing machines. And before we get there, I'll start with what a Turing machine is. So your computer is a Turing machine, or an example of one. And it's just anything that takes in a sequence of numbers or information and turns it into an output. So it sounds exactly like how I described the neural network, because that is one way of solving problems. It's essentially a very general way of saying something that solves problems. So a neural Turing machine, and the classic example of a Turing machine is, because this was invented in like the 30s by okay, I'm blanking on his name, which is pretty sad, but Turing, Alan Turing, there we go. Okay, so anyway, his example, because he was in like the 30s, was like a tape, and he also invented the first computer. So that gives you some context. It's like a tape of or just a piece of paper, and it has a bunch of ones and zeros, and you have some thing that scans over the top of it and reads what the number is, and then decides whether it wants to change it to a 0 or a 1 or leave it the same. So that's one way of solving like the problem of turning something into something else. So then a neural Turing machine kind of takes from that example, and it gets this external input like a normal neural network would. And then it has this controller, which is where the machine learning really comes in, and it can decide to write to this memory, or it will read from it, and then it can decide whether or not to write to it, just like a Turing machine. And this is interesting because normally in machine learning, we don't explicitly have an external memory that we're using to represent things that we want to remember. We just, like in the case of recurrent neural networks, remember things in the hidden layers and the weights that we have trained. So in this case, the weights that we've trained, they're in the controller, but we're remembering things in this explicit memory. So that's where it's a bit different. So a bit of a closer look at this diagram. And the key idea of a neural Turing machine is that when you have a larger explicit memory, you're going to spend more time on computation because there's more things to read and write to. So even though memory doesn't in itself mean that you have to do more computation, it generally does correlate very highly with more computation. And if you have a really big memory, how are you going to read that whole thing every time and decide what to write every time? However, if you have attention and you select specific parts of the memory to pay attention to, that can help a lot. So like when you're learning how to play like a sport, you don't need to be remembering your homework probably to learn how to do that sport. So your attention with respect to your memory might be on, a past game that you played that was similar to the sport. That might be more useful to remember. So you can see how the brain might do something like this as well. So that was a very brief overview of a neural Turing machine. And then what I want to turn the attention to is how all of these things that we've talked about might correlate, especially in deep learning, might correlate to things that we do with our brain. So some questions for consideration are, there's different ways of attending to things. You can attend to your memory, or you can attend to, you can literally turn your head. And when you turn your head, that changes your attention because you're no longer looking at the same thing. So you're limiting the sensory input that you get. So that's one way of attending to something, is like limiting the sensory input. And then another is just like focusing on something else. So focusing on your homework instead of, distractions around you or something like that. That's another form of attention. And do we represent these well in machine learning? What are we missing in that case? And is memory really similar to attention over time? Are these the same mechanisms? I think based on what we've heard about the brain, the hippocampus has a lot to do with consolidating memories, but it doesn't say much about whether this has to do with attention. So over here is like a lot of the neural correlates of attention, and you don't see the hippocampus. So is this claim that memory is attention over time, is that accurate? Perhaps, I don't know. And so finally, we have a couple discussion questions, and we were thinking we would do breakout rooms, but if that's not possible, we can just leave these for thought. I don't know what you guys want to do.
Yeah, sorry. I guess maybe there's all no lobby right now, so we're gonna skip it for now, maybe.
Okay, we can just talk about them, and hopefully people will consider them on their own. Yeah, Janet, do you want to go over some of these?
Yeah, I remember like the flow chart that I showed earlier. So attention is basically a mechanism of sensory memory. So in my opinion, I feel like if you have like repetition of attention, then that would, go to long-term memory for sure. So that attention over time thing leads to long-term memory, in my opinion.
I guess I could also just like ask a question right now to like kind of get the audience thinking. So, Chaitan, you brought up like attention in both like neural networks and brains. So, I was just curious, like, is there a way for like Turing machines to be able to like switch attention instantly, just like our brain can? So, like for example, let's just say, like I'm playing soccer, I'm like focusing on dribbling the ball, but then all of a sudden like a hurricane starts, and my brain would automatically just like switch my attention fully to surviving a hurricane, right? But could a neural network do that, or is it like not something we can do right now?
Yeah, okay, that's a really interesting question. So the answer is kind of. I mean, so a neural Turing machine doesn't represent all of the things that would happen in your brain when your attention switches like that. Like if you see a hurricane, all sorts of different hormones that control all different parts of like both your like neurological attention and as well as like your physiology are going to start like taking over. And neural Turing machines don't model all of that. But let's say you have some part of this like little memory tape that you have written to. You basically would have to have seen something similar to like a hurricane or something like that before, and then because what this is focusing on is attending to things like that you've written to memory. So in that example, if your attention turns to like the hurricane, it only really makes sense in this context if you start remembering something about a prior hurricane or something, because what you were talking about is maybe like changing your sensory input towards the hurricane, whereas this would be talking about changing what you're thinking about towards the hurricane. So let's say you have seen something similar that to like natural disasters or something, and you've written to it in this memory, then this would go and attend to that instead of whatever else it was doing. But it's again pretty rudimentary and not very similar comparatively to all the mechanisms in your brain that would start going off in that scenario. But yeah, good question. Okay, so a couple of our other questions is remembering back to the large language models, such as like transformers. How should we represent memory? Should we use something that is more more certain in our representation than a neural network? And does the fluidity of a neural network's representation of memory allow it to address more complex questions, like like language is complex, whereas remembering what 2 plus 3 is can be represented very simply. And then our final question is sort of, in what ways are humans related to all these deep learning models of memory, and how well do they actually capture what humans are doing? So that's a very difficult question, and we don't even know the answers. We're just very interested in it. So yeah, in summary, the things that we have gone over are the attempts to model memory in deep learning, and they have all greatly advanced machine learning, regardless of whether they correlate to what the brain does. And then we went on to discuss what the brain does to store memories, and both short-term and long-term memories, as well as like the structure of the hippocampus and how that plays a role in that. And then finally, we talked a little bit about how we can try to bridge neuroscience and AI, and how this is an extremely difficult but also extremely valuable task. And that's sort of like what our team is all about. So cool.
Yeah. Okay. I guess we have some questions. Okay. So I'll just ask them. Whoever wants to answer can just answer. So let's see. So is there a benefit in trying to imitate a human brain? Like, would it be possible to design a neural network that would maybe do it better than a brain? Because maybe like evolution hasn't run its full course, and maybe our brains like there's probably stuff that we can improve, right? So is it possible, or are we just like trying to imitate the brain right now?
Sure. Yeah, that's a super interesting question. So the thing is neural networks that try to imitate the brain are always like, well, I won't say always, but very often focus on one specific aspect of the brain, because the brain is not fully understood. So even if we wanted to imitate the whole thing, we can't right now. Also, neural networks are a fundamentally different substrate than the brain. So the way neurons work in the brain is they either fire or they don't. And then they have these things called dendritic synapses, which most neural networks don't even model at all. And whether or not they, there's all different ways of wiring them. And then the way that you learn is another part of it. So the way that neurons get rewired in the brain is different than how we rewire them with neural networks. In neural networks, we use a thing called back propagation usually, which is a lot of calculus and things to calculate how you want to change weights in a neural network. So this works very well, but there's little strong evidence that the brain does that. It certainly does not do like some calculus before it updates how neurons are wired. So attempts to model the brain, right now we can't, but is there a benefit to doing that? Yeah, so as we presented today, like all sorts of neural networks take inspiration from different aspects of neuroscience. And each one claims like it's getting closer to human-like intelligence. That's very debatable, but I'll leave that for your own opinions. And could we ever get something past human intelligence? Like do we have to model the brain to get there? I mean, this is purely opinion, but I would say, not necessarily, but the only thing that has shown promise so far is looking at what we do, what our brains do, and the things that our brains can do that are miles ahead of what we can do with computers, and trying to figure it out from that. It's a natural starting point, at least.
Oh, and like what Chayton said, just to add on to that, computer scientists find inspiration from neuroscientists, and also neuroscientists find inspiration from models made by computer scientists. And also to understand the brain, I think it's very important. We can't just have neuroscientists studying the brain. We need the collaboration of all physicists, like mathematicians and computer scientists, to come together. So yeah, that's just what I wanted to add.
Yeah, that's a great point.
All right. Another question. So are there any cases where like neural network models like the recurrent layer or LSTM, are there any cases where they'd be like more efficient for like certain tasks, or like are they currently being used in real life because they're like faster than like maybe more complex ones that use long-term memory?
Is this like in comparison to a transformer?
Yeah, I think.
I mean, people certainly still use recurrent neural networks and LSTMs. It's just kind of pretty sharply fallen out of fashion just because transformers are, I mean, computationally wise, they're better. Usually, I'm not an expert in the run times of either of those. I just know that if you take something, the example we showed of the large language models was from GPT-2, which is a now outdated but still very powerful transformer model, and they just perform just results that you cannot get with an LSTM or an RNN because they just don't have this problem of forgetting. So, but RNNs are conceptually, I think, simpler to understand, so people do still use them.
All right. I guess one more like subject specific question, then we'll go into like the broad questions. So, let's see. Yeah, so there was like the example that Jana talked about for what was it, the person, I forgot their name, but they had a missing hippocampus and then they couldn't form any like long-term memories anymore. So I was thinking like, if we have like organ implants for like the heart or like the lungs, would it be possible to in the future maybe using like, I don't know, some more complex 3D printing, would it be able to recreate a hippocampus, like melding both like the neural networks using like a computer, or like you'd create a neural network to copy a hippocampus or like imitate it, I guess, and then you could implant it into a person and it would like work just like a normal hippocampus. Would that be possible?
That's a very good question, and I really hope it is possible, and I hope we have a positive future in regards to that. But I also wonder how that new implant can retrieve like older memories, like the memories you had when you were a child, for example. Like how would that new hippocampus do that? So I'm not sure.
All right, no worries. Okay.
Wait, I want to add on. So that was a super cool question. And I also don't really know the answer because that's such a cool question that people don't really know how to do it. But I would say I worked in a lab and we made organoids. So if you want to check out something cool, check out cerebral organoids, because that would be like making, a part of the brain. They're definitely not there to where they could make a specific structure in the brain yet, but it's pretty cool.
Yeah, also I think they can form maybe new memories of that new hippocampi, but probably not retrieve old information, the ones that you had before you put in that hippocampi. So
Okay. I guess now like the boring questions. So, um, what made you guys like decide to join or like create the Interactive Intelligence Club at UW?
For me, it was like I was really interested in human-like intelligence, not just machine learning that could go classify pictures and stuff like that. And I just was having trouble finding people that were also interested in that. So I was like, well, I'll just make a place where all the people gather to do that. And then Jana, you can speak to, I don't know, how you joined.
honestly, I saw a flyer and I thought it was super cool. Such a like a new novel idea, and it's not a workshop, but a club I've never actually seen before at UW, and Chayton came up with this brilliant idea to create it. So I first joined their Discord just for fun, and then he was looking for admin members, so I just signed up for it, and here I am now, and I love it so much.
Nice. Okay. Um, let's see. Also, just like what initially made you guys interested in like the field of artificial intelligence or like neural networks or like just neuroscience in general?
For me, I think it's like something that I can see is going to change the world very rapidly and quickly. It's a problem that obviously has a lot of work to do to be solved, and that's like I want to learn more about it. So that's I want to understand the things that are going to change the world. So that's for me.
Yeah, and likewise, neuroscience is like a fascinating subject in itself, and I feel like everyone finds it quite fascinating because our brain is in our own bodies, yet it's such a mysterious thing. Like we barely have an understanding of our brain, even though we all own one. So I think, that wanting for discovery and just curiosity towards the brain made me go into the neuroscience major.
All right. Let's see. So for you guys, like, what do you think is, like, personally, what's like the biggest challenge in researching or just like understanding the link between neuroscience and AI or like neural networks?
Oh, I think I can go first. There's a lack of collaboration and communication within different fields. So I feel like, neuroscience shouldn't just work amongst themselves, but they should actually collaborate and communicate with, computer science people and physicists and mathematicians. But I feel like right now there isn't that much collaboration and connection. So that makes it a little bit more challenging. And even in my major, a lot of my fellow students in the neuroscience major are not very much integrated into things like machine learning. So they have little knowledge about that as well. So I think that makes it more challenging.
Yeah, I completely agree with that. I would also add that I think machine learning has developed very rapidly, but not in ways that reflect truly intelligent algorithms. And I think the reason for that is because there isn't a very large profitable incentive for companies to focus on human-like intelligence. Well, I mean, there is, but it's such a broad long-term goal that it's not something companies focus on. They focus on things that will immediately provide them results and target your data better for ads and things like that. And so AI is very frequently used for just things that you typically would use a classical computing algorithm for. And so it's developed a lot and gotten a lot of funding for that, but it just hasn't gotten a lot of funding for people with broader goals about what they want to see from machine learning, and that includes collaborating with people interdisciplinarily through things like neuroscience, because that takes time and it takes patience, and both fields are underdeveloped in that respect. So yeah.
Okay. I know there's been a lot of questions, but final question is just like, do you have any general advice for any middle or high school students who are like tuning in or just like watching the recording later on, looking to enter the field of neuroscience or like neural networks?
Yeah, I think, I guess for me, being around a lot of computer science people, I would say just don't get distracted by the shiny things all around you. Just follow the things that have always made you really passionate. Because computer science is a place where you can easily get distracted by just all kinds of emerging opportunities and things you have to do, and it's so broad. But if this is something that really interests you, don't forget about it. Yeah.
Yeah, that's a really important point. As someone in the neuroscience major, I would like to point out that just don't be discouraged based on how complicated and difficult the courses are. I struggled so much throughout my undergraduate years. The courses were intense. However, I think I still kind of made it through. I'm going to go into my last year in college. And although there are so many times where I wanted to just give up and go into some other major, for example, but just be persistent and be yourself, and also spend a lot of time with your family and friends. And just don't forget about the other important priorities as well.
All right, thank you so much. And unfortunately, that's all the time we have left today. So I'd like to end off by thanking Chetan Inman and Jenna Hong for taking the time to lead a workshop for us today, and as well as Andre Ye, who helped make this presentation. And thank you all for attending today's session with PTC Seattle, and we hope you had an amazing experience. And if you have any questions, feel free to reach out to us on Instagram at PTC Seattle. And yeah, so once again, thank you so much for taking the time to participate in our track of artificial intelligence.
Thank
So,
you.
Thank
you
you.
for having us.
Bye, guys. I'm going to end the meeting now.
All right.
See you.